Hello, fellow problem solvers. So today we're going to be doing a problem from the 2011 IMO Shortlist, problem number C2. This is a viewer-suggested problem, which I suggest you take at least an hour, ideally 2 hours, but not more than 3.5 hours. If, on the other hand, you would like to go along with us, I suggest you take half an hour and write a bunch of ideas out on paper. And now, let's begin. So in summary, we have 1,000 students on a circle, and they are either girls or boys, and we must prove there exists an integer k such that we can pick 2k students, consecutive students, such that the first k of those 2k students and the second k of those 2k students have the same number of girls in those two groups. In the first k, there's the same number of girls as in the second group. Now, the easiest way to really sort of make this algebraic, really just make it concrete, is to call these students S1, S2, all the way till S1000, and Si is equal to 1 if boy, else it's a 0. That way, the condition is that Si plus 1 plus Si plus k minus 1 is equal to Si plus k, all the way till Si plus 2k minus 1. This is the condition with S1000 plus I is equal to Si, and this is also equal to Si minus 1,000. So now the problem statement is really show there's a case such that this is true no matter whether Si is 1 or 0, whatever the ordering of girls and boys on this circle. Now, with this in mind, the question is, what can you really do? Well, let's see. Say we look at consecutive sums. So we take the first k and the next k. K, S2k minus 1. For some k, it doesn't really matter which one at this point. Actually, this is S2k. So we have this thing, this sum, minus this sum. And see, we look at the differences between these sums. Now, the difference between, say, if this one has A, this one has B. Okay, and then we move them by 1. Then we do this sum and the next sum till S2k plus 1, sk plus 2. And this is really just me messing around, seeing what happens. And this is also a common strategy, somewhat, that I've seen, is just shifting by 1 and seeing what are the possible changes that can happen between these groups. Like if these things on a circle, you shift by 1 and just see what are the possible changes. And the possible change here is really if this is 0 and this is 1, then this will become A plus 1. And if this is 0, this is 0, this will stay A, or 1, 1, it will stay A. If it's 1, 0, it will become A minus 1. So we know that, and similarly for this. Now, the question is perhaps what happens when this is, say, 0, 1, and then B. With B, it could either stay B, or it could stay B minus 1. If this is 0, this is going to be B minus 1 now. If it's 1, it's still going to be B. If we have A, we could have either 0, 0, 1. Then this is going to be B plus 1 or 0, 1, 1, 0. So it's either, I think this can be anything, if I'm not mistaken. B minus 1, B plus 1. And with A minus 1, that's if this is 1 and this is 0, then what can this be? If it's 0, it stays B. If it's 1, it's B plus 1. Wait a second. If it's 0, it stays B. Yes, B or B plus 1. I think I made a mistake somewhere, but now what I invite you to do is to play around with this for about 30 minutes, push it, and see what it is you get. Here's my next step. So the first sort of idea that I was getting here is let's look at two consecutive sums of k, which have the smallest absolute difference. The smallest absolute difference for some k will be equal to 0. Let's take a k, doesn't matter which k, we'll figure it out later, but let's take this one with the smallest difference, absolute difference between this sum and the next sum. And with this, I couldn't get any luck. If this is A plus C, and this is A, then I couldn't really get to a point where if this is now, say, 0, if this is 1, and if this is 0, then the next sum after this one will be A plus C plus 1, and this one will be A minus 1. Like, I'm not going to get anywhere closer with my solution. So I scrapped that, and then I looked at the next idea. Okay, let's just try to get at this smallest sum on another way. Let's take the sum, the I for some k, such that Si through Sk, this sum is the largest sum of k consecutive s's for all I. And now what this gives us, if this is the largest thing, then we look at the one previous to it. This is si minus k, and the one after it, si plus k. Now this minus this is negative, but this minus this is positive. So at some point, as we're moving by 1, there has to be a change from the difference being negative to the difference being positive. And if you look at the sum of these two consecutives, if this is b, let's call this sum b. B, let's define it by b of k for I is equal to si plus 1 all the way till si plus k minus 1, like the number of boys. And the thing is that bk of I minus bk of I plus k, this thing changes by at most 2 at any point. The absolute value of this changes by at most 2. And it only changes by 2 when we have 0, 1, 0 or 1, 0, 1. So now given this changes by 2 at most, there must be a point at which it is negative and then it becomes positive, i.e. there must be some k, some I and some k, such that we have this sort of situation. This is a and this is a plus 1. And then when we're at si plus k minus 1, si plus k, this is si plus 2k, si plus 2k minus 1. So it goes from a and a plus 1 to the next one being a plus 1 and this one being a. There must be a change like that. And because there must be a change like that, the only way this type of change takes place from a to a plus 1 is if this is 0, this is 1. And from a plus 1 to a, this must be 1 and this must be 0. And now here I invite you to take, say, half an hour and figure out what would you do next. Here's my next big idea. So this is what we have. We have si 0. Then we have the next from si plus 1 till si plus k minus 1. The sum is a. Then we have 1 and then another k minus 1 of them whose sum is a. Now the question is, under what circumstances, assuming k is small enough, would I be done? Well, the question is, what is si minus 1 equal to? Under what circumstances am I done with si minus 1? And this is a common sort of strategy when you're solving any types of problems really, is that you're looking at under what circumstances am I done with the problem. And if in circumstances A, I'm done with the problem, then the only thing I need to look at is circumstances where I don't have A. And that might be an extra condition that we can work with to further progress and solve the problem. So here, what we have, so we have the sum from bk, I is a, bk, I plus k is a plus 1. And we also know that bk plus 1 of I plus k is also a plus 1 because this is 0. And bk of I plus k is from here to here, just before this point right here. So what does that mean? So we will be done if k plus 1 is okay, and if bk plus 1 of I minus 1 is equal to a plus 1. We're done in that case. And when will this be a plus 1? Well, it will be a plus 1 when this thing here is 1. So, with that in mind, I invite you here to pause and take 10 to 20 minutes and see what would you do next. How would you push towards a solution or potentially another idea? And here's the thing, namely, if si minus 1 is equal to 1, we'll be done because then this will be a plus 1. So let's assume we're not done. Let's assume we can't be done. And then that means si minus 1 is 0. And then with that in mind, we can also look at, okay, from bk plus 1 of I minus 1, this whole thing here is a. Now, if you look at what that is starting from here, ends here, and this thing from here to here. Now we can look at the next thing, namely, we look at si plus 2k plus 1. Because what's the thing? we have that now bk plus 1 of I minus 1 is equal to a. So this whole sum here is a, and this whole sum here, bk plus 1 of I plus 1, is a plus 1. So now, with that in mind, if we just push this, started from I minus 1, we say b of k plus 2, starting at I minus 1. This sum here is going to be equal to what? It's going to be a plus 1. But the sum starting bk plus 2 of I plus k plus 1. So it's the one starting from here. Actually, let's just look at this for a second. This ends at this plus this minus 1. Let's take a pause here. Oh, my bad. I do not need to increase k to k plus 2 just yet. No, we can just look at bk. Actually, we need to look at bk plus 1. Starting at I, this thing right here is going to be equal to a plus 1, and bk plus 1, starting from I plus k plus 1, this thing right here is going to be equaling. So it's starting from k plus 1 and ends here. So it's going to be equal to a plus si plus 2k plus 1. So we will be done in what case? Well, if this thing right here is a 1, we will be done. So let's assume we're not done. Let's assume the contrary. It is 0. And now we can continue doing this, going back and forth. 0, 0, 0, 0, expanding the number of zeros we have. And with this idea, I invite you to pause for another 10, 20 minutes and try to finish the problem up. Here's the finish. So this is where we're at. Si is 0, Si plus 100 is 1, Si plus 200 is 0. And we have this, we're looking at that I, and we're assuming the contrary, i.e. b of 100 plus j of I minus j isn't equal to b of 100 plus j of I plus 100 for all j from 0 to 200. And we're going to prove inductively that b of 100 plus j of I minus j is going to keep equaling a. And at the same time that b of 100 plus j of I plus 100 is going to keep equaling a plus 1. So now we do this induction. The base case holds for, and we're going to do this induction over j. So the base case holds for j equals 0. That's just our setup right here. Assume it holds for j equals k. What that implies for our k is that si is equal to si minus 1 is equal to si minus k. 0 for that k, and si plus 200 is equal to si plus 200 plus 1 is equal to si plus 200 plus k is equal to 0. And the way I'm just like finding out these indices is just by looking at small cases. For j equals 0, you already have it. That means these two things are 0, and for j equals 1, I checked it out. So that is just like the way I figured out what the indices are. And now what we do for j equals k plus 1 less than or equal to 200, keep in mind that we have that b of 100 plus k plus 1 of I minus k plus 1 is going to be equal to b of 100 plus k of I minus k plus s of I minus k minus 1. And to show that fully, we know this via induction is going to be equal to a plus si minus k minus 1. Now, on the other hand, we know that b of 100 plus k plus 1 of I plus 100 is going to be equaling what? Well, via the inductive hypothesis, this is going to be b of, actually not an inductive hypothesis, but just using this plus si plus 200 plus k, and this right here is going to be equaling a plus 1. And now, if these two things are not equal, then we have si minus 1 minus k is going to be 0. And we prove a similar thing with the other one. But this also just like points to a fact that maybe we should work the induction on this and have the other thing, have this thing be a consequence of this. Maybe that will be our induction in the actual solution. And now with that, what will we have? Well, we will have that Si is equal to Si minus 1 is equal to Si minus 200 is equal to 0. And also on the other side. And with this, I invite you to take 5 minutes and see what's the next step. And the next step is basically that this just implies that we have B of 100 of I minus 200 is going to be equal to B of 100 of I, what do we have? I minus 100. And with this, the problem, and this is also going to be equal to 0. And with this, the problem will be solved. So now I invite you to take 20 minutes to maybe write up this formally as a solution, because that's what we're going to be doing next. So we begin with these definitions. Let the people be S1 through S1000, with S1 being 1 if Si is a boy and 0 otherwise. And Si is equal to Si minus 1000 is equal to Si plus 1000 for all I that are in the range. And now, and let also be K of I be equal to Si plus Si plus 1 plus Si plus K minus 1 all the way till here. And now what we need to prove is that there exists a K between 100 and 300 and an I between 1 and 1000 such that Bk of I is equal to Bk of I plus K. The way we prove this is using the external principle, namely, we first use the I max, which is the I with the largest B 100 of I, and we use that to say that B of 100 of I max minus 100 is less than B 100 of I max is greater than, and this thing is greater than, B of 100 of I max plus 100. And now given that the difference between any two consecutive I's for B sub 100 of I minus B sub 100 of I plus 1 is either 0 or 1, this means, given this, that if B of 100 I isn't equal to B of 100 I plus 100 for any I, then there exists a J between I minus 100 and I, such that B of 100 J is less than or equal to B of 100 J plus 100 minus 1, and B of 100 J plus 1 is greater than or equal to B of 100 of J plus 101 plus 1. And the way we know this is because we are looking at the function B of 100I minus B of 100I plus 100 at I equals I max minus 100, this thing is negative. At I equals I max, this thing is positive from here. And because this function changes by either 0, 1, minus 1, 2, or minus 2, we know that there exists a place where it changes signs. And for that place, we know that we will have these inequalities. And in that place, we know that we will have these inequalities. And from here, we can basically infer that Sj, for this j, is equal to 0, Sj plus 100 is equal to 1, and Sj plus 200 is equal to 0. And now, given we have this, the next step is let k and l be positive integers such that Sj's Sj minus 1 is equal to Sj minus k plus 1 is equal to 0. And Sj plus 200 is equal to Sj plus 200 plus 1 is equal to Sj plus 200 plus L minus 1 is equal to 0. Mind you, if K or L is 1, then we're done immediately with this. And such that Sj minus K is equal to 1 and Sj plus 200 plus L is also equal to 1. And given we have symmetry, we can assume without loss of generality that K is greater than or equal to L. And now we have two cases. Case 1 is K greater than or equal to 200. Now this implies, given this, we will have that B of 100 of J minus K plus 1 will be equal to B of 100 J minus K plus 101 is equal to 0. And we're done here. And the second case is that both K and L are less than or equal to 200. And in this, actually strictly less than 200. And in this case, what we have is that Second case, 200 is less than k is less than or equal to L. And here we have that be L plus 100 of j minus L plus 1 is going to be equal to BL of j minus L plus 1 plus B100 of j plus 1. And this thing right here is equal to 0 plus 100 B plus B of 100 j plus 1 is equal to 0 plus B of 99 j plus 1 plus S 100 plus j, which is 0 plus B 99 of j plus 101 plus 1, which is equal to this thing right here plus Sj of 200 plus L, because this is 1, this is 0, and this thing right here is equal to B of L plus 100 of j plus 101. Now, given L is less than 200, we know L plus 100 is less than or equal to 300, and we have proven that there exists a k, namely L plus 100, such that L plus 100 of j minus L plus 1 is equal to B of L plus 100 of j plus 101. And as always, thanks for problem solving.